In this problem, we again meet our old friend, the cable under tension. But there are some new aspects here. So let's take a minute to read the problem, and then let's solve it step by step. So as you see, we now have a two random variable problem, and in addition to y, the load q is also a random variable now. Y and q are independent, and it so happens that both of them are normally distributed. We need to solve the problem, not only find the failure probability, but make sure that it does not exceed 0.001 by choosing the appropriate cross-sectional area A, which is non-random. Now, here is an interesting question, that there are different ways of describing failure. They should be equivalent. We could define AY less than Q. We could define AY minus Q less than 0. We could define AY divided by Q less than 1. We could we could take log. Obviously, taking log would be a problem because y and q also have negative values. But this is a general representation. Now, which one of them would be easiest to solve, or would they give different answers? And if so, then can we impose some invariance conditions? Can we do something so the answer is invariant to the way we describe failure? These are questions we are not ready to answer yet, but these are important questions. For now, we see that because y and q are normally distributed, it makes most sense to take a failure representation which is a linear combination of normals. So AY minus Q would be the most logical choice for the limit state function, and that's what we do. From that point on, it becomes a one variable problem in the cross-sectional area A, because we are putting all the values of the mean and variance of y and q. So in the end, we have to solve the problem that the failure probability is 0.001, and that gives me the answer for A. It's 51.5 square inches. So this tells us how to not only set up the problem, which we have done in the past, but now we need to think beyond that and see how to solve it. And here we were lucky. The problem could be formulated in a manner that we could solve it in closed form just by estimating the normal CDF. Here we stay with the same problem but put a little twist. This is what we are calling example A2, and if you just read it carefully, you will see that there is one difference from example A1, is that the distributions of y and q are each log normal. So it is probably going to change the answer, but we need to set up the problem properly and solve it. So let's take a few seconds to acquaint ourselves with the problem statement, and then we will proceed with the solution. So here again the question as to which failure representation to take. Because y and q are log normal, it seems the obvious choice is the last one, which is involving log y and log q, because we know that they are each normal and we very much like to have a linear combination of normals. So we take the safety margin, as I just said, And now it's again straightforward. We have solved such problems before. We come up with the statistics of M in terms of A, the unknown cross-section area, and impose the condition that the failure probability is 0.001, and that gives us an answer slightly lesser than the previous case. It's 45.6 square inches. Now, let's confront this question now because it's something we are going to deal with quite a lot. Is that what if we did not have the benefit of such simple closed form solutions? What is the problem formulation or the distributions were such that this nice simple analytical solutions were not possible? What should we do? And we have one example here. If suppose y was Weibull and q was Gumbel. What if the area was also random? So then we have situations where simple linear combination of normals is no longer applicable. But we still need to solve such problems, and that is why we are going to look at approximate solutions. And in particular, we are going to look at solutions, approaches of the type where we would like to estimate the probability content given a limit state equation in terms of basic variables of arbitrary size and arbitrary distributions. And what we are going to look at in the next few lectures is to be able to compute the failure probability for such a situation analytically, exact, which we actually did. One or two examples. Approximations, the very elegant first order reliability method, its a little more complicated cousin, the second order reliability method, SORM, and then simulation based approaches, both direct or brute force Monte Carlo simulations, which we have alluded to in the past, and at least one variance reduction technique, the importance sampling method.